Hello, everyone. My name is Sheraz Bashir, and I'm a final year PhD student here at Clarkson University. Today, I'm going to talk about my research on electrochemically driven production of an ammonia-loaded biochar alginate composite as a slow-release nitrogen fertilizer. First of all, why ammonia recovery matters. All of us, we knew that nitrogen fertilizer demand is increasing due to the growth in the population, but its reliance on the Haber-Bosch process makes it energy intensive, which is unsustainable. Meanwhile, the ammonium in the wastewater, it has the potential to meet up to 30% of the global fertilizer demand. That is a huge number. Therefore, it is important to recover this ammonium from the wastewater by using some sustainable recovery method. The conventional electrochemical ammonia recovery approaches, they are quite promising, but they also comes with some limitations, which includes the membrane stripping, which is the expensive step, as well as they also need some additional chemicals for the acid absorption step. Therefore, it is critical to develop some sustainable ammonia recovery strategies in order to advance environmental protection as well as the nutrient circularity. In this work, we propose a sustainable and circular approach that converts wastewater nitrogen source into the value-added slow-release fertilizer. This approach combines electrochemical ammonia stripping with the gas phase ammonia absorption onto the low-cost biochar alginate beads to enable direct ammonia capture from the wastewater. The key innovation here is the use of cost-effective adsorbent to directly capture electrochemically stripped ammonia, replacing the expensive membrane stripping and subsequent acid absorption, thereby promoting resource sustainability and circular economy. The first step here includes the preparation of the biochar alginate composite beads. And the biochar was modified here by using phosphoric acid by following one of the recipe quoted in the literature. The second step is the separation of the ammonia by using electrochemical flow cell. And this is the two-compartment flow cell, which is separated by the cation exchange membrane in the middle. And these are the actual experimental conditions used for this electrochemical separation of ammonia. Based on this pH profile, the red circle, they represents the pH on the anode side compartment, and the blue circle, they represents the pH on the cathode side compartment. Due to the production of the hydroxide ions on the cathode side, the pH on the cathode side was increased. And due to this higher pH, the ammonium in the wastewater was converted into the ammonia gas. The third step is basically to adsorb the electrochemically separated ammonia from step number 2 onto the surface of the biochar alginate beads. So this is the absorption mechanism. Due to the moisture film around the surface of the biochar alginate beads, the ammonia gas was dissolved into the form of ammonium ion. So these ammonia-loaded beads, they were dried overnight, and then these dried beads, they were soaked back into the deionized water in order to study their slow-release nitrogen behaviors. Here we compared two phases, the one gas phase and the other one liquid phase adsorption behavior of the beads. For the liquid phase adsorption behavior, the beads, they were directly soaked into the 50 millimolar ammonium chloride solution, and then they were dried and re-soaked again into the deionized water to study their nutrient release behavior. The results from ammonia release in DI water show that the gas phase ammonia adsorption is highly effective in terms of slow nutrient release compared to the beads from the liquid phase adsorption. So this slow release nutrient behavior from the gas phase adsorption shows that the air stripping can be successfully coupled with the adsorption. In conclusion, overall, this study presents a scalable and chemical-free nitrogen recovery strategy. The biochar alginate composite beads, they not only improve the absorption efficiency, but they also enable the nutrient reuse with reduced losses. Or further, we can say that this work bridges the wastewater treatment and agriculture by transforming a pollutant into a value-added slow-release fertilizer, moving us closer to a circular and sustainable nitrogen economy. Thank you.